What we're going to talk about today is what's called conditional probability. Very important topic. And in some sense, this really underlies the probabilities that we often encounter in real-world engineering problems, right? So a lot of times we're faced with a question in the real world about something along the lines of, what's the probability of this thing happening given that I saw that this other thing happened, okay? Because in many real-world situations, we can't directly observe the thing we're trying to reason about. We only see some sort of a symptom that's related to the thing that we want to really know about, right? So for example, you know, any kind of medical diagnosis problem, right? Given that this test was positive, what's the probability that the patient has the disease, right? So things like probability of, we want to know, we want to know what is the probability that the patient has the disease given that the test was positive. Or something like, you know, given that, you know, what's the probability that the network is congested given that it took me, you know, X hours to download this, you know, torrent. Not that anyone torrents anymore. Or something like in a communication system, you know, what's the probability that, you know, this message was sent given that this is the message that was received, right? Because we know that in real-world communications channels, symbols get mixed up a lot. Again, kind of in the more, you know, kind of machine learning-y world, you want to know, you know, what's the probability that, you know, this picture contains, what is this picture of? I don't know. He's going to give these guys some arms. You know, so what's the probability this picture contains your friend Bob, given that I know there are humans in the picture? So, you know, usually we have some sort of side information. We want to know how is the thing that we care about kind of related to the thing that we observe, okay? And so in all these cases, we usually frame the problem in terms of a new probability notation that we haven't talked about yet, which is the probability of A given B. So whenever you see a straight line like that, you kind of read it in your head as given, okay? What's the probability of event A given that event B occurred, okay? And it's actually pretty easy to reason about this probability. Everything that we're going to do today kind of follows from one very simple probability observation, which kind of is based on what we talked about last time, right? So if I have two events A and B, right? So here's A and here's B. Right, so now I tell you that B occurred, right? You know that you're somewhere in that blue circle. What's the probability then that A occurred, okay? And so kind of intuitively, it's related to this intersection, right? So this green area is A intersect B. And if I tell you that B occurred, in some sense, it's like we're narrowing our attention. We're changing the sample space to be the whole thing down to just B. And now I want to know, okay, I told you that B happened. What's the probability that I'm inside this stripy region, okay? So to say that a little bit more mathematically, the probability of A given B is the probability of A intersect B over the probability of B, as long as this probability in the denominator is greater than 0. Right? It's kind of, hopefully this makes a little bit of sense. This is like saying that, you know, I tell you that B occurred, and so instead of looking at the overall probability that I'm in this region, I kind of normalize, I divide through by the probability of B. That again gives me something that's between 0 and 1, okay? And so let's think about some circumstances where knowing B tells me something about A, right? So for example, suppose that I'm in a situation like this, where I've got, again, using the same color notation, I've got A and then I've got B. So in this case, if I tell you that B occurred, then for sure A did not occur, right? Because A and B are disjoint. So this is like saying that, you know, if this is A and this is B, then the probability of A given B is equal to 0, right? There's no intersection between these two events, so if I tell you that you're in the blue circle, then you're certainly not in the red circle, right? Impossible. So here, knowing B gives me kind of full information that A could not have possibly happened, right? Kind of the opposite of that is something like this, where I've got B, and then I've got, I'm sorry, did I draw this wrong? I did draw this wrong. Scratch this. So here, B is going to be this guy, and then A is going to be entirely surrounding B, right? In this case, the probability of A given B is equal to 1, right? Because if B happened, then for sure A happened, right? A totally surrounds B. So, you know, it's like saying, you know, what's the probability that, you know, you rolled a even number given that a 2 was rolled, right? 1, because even number is a bigger set than 2. So telling you 2 immediately gives me full information about A, right? Or kind of in a more real-worldy case, right? If we suppose that the sample space is kind of like the set of all, you know, humans, it could be that A and B are both really tiny. So this is kind of just for dramatic effect. These are really small red and blue circles, right? So in this case, you know, the probability of A and the probability of B are both very, very small, right? So for example, think about, you know, B being this really obscure medical test coming back positive, and A being the probability you have some sort of really rare disease. Okay, so both those things by themselves are very unusual, but if this is a really good test, the probability of A given B is large, right? Could be close to 1 because those circles overlap. That's like saying that, you know, if this really weird test comes back positive, then I can be very, very sure that you're likely to have this disease, right? So this is like a kind of a rare symptom, rare disease kind of situation. On the other hand, you could have something where knowing that B happened doesn't really give you very much information about A at all, right? So let's again use our kind of like notation where let's say that A is the top half of this sample space, and B is the left half of this sample space, right? So here, this is a situation where the probability of A is equal to a half, just by geometry. The probability of B is equal to a half. And now I tell you, okay, B occurred. You're in this blue world. Now what's the probability of A given B? Well, that double-hatched region makes up half of this subregion, right? So the probability of A given B is still a half, right? Telling you that B happened didn't actually have any sort of impact on my understanding about whether A happened or not, right? So let me pause and ask. Comments or questions about this? Yes? Okay, so a couple things. So you used a magic word called independent, right? So we didn't actually introduce this concept yet. So we're going to talk about the concept of independent events coming up. So don't worry about that. So I think the intuition here should be, yeah, so let's not go there quite yet. Okay, we are going to get into this concept of what does independent mean, right? Kind of intuitively, what we're talking about here is that, you know, B doesn't shade any light on what's going on with A. Even though, you know, these two events may not necessarily be independent, but it's more about probabilities than expected values, which is more of an independence thing. So let's put a pin in that. We'll come back to that concept in a few lectures, okay? Other questions or comments? Let's do some concrete examples to make this a little bit more explicit, okay? So let's suppose that we do the usual thing of rolling 2 dice, okay? Roll 2 dice, and then let's count the sum, okay? So I'm going to make my table of die rolls and sums just for reference. So this is die number 1, this is die number 2, and I'm just going to add these guys up. Had a brief moment of conscious, am I doing this right? Of course I'm doing this right. Okay, so, you know, we're going to assume that each of these, you know, dice is fair, which means that the probability of each of these things happening is 1/6, right? No funny dice, okay? And then I can ask something like, you know, what is the probability that the second die is even, given that the dice sum to 4? Okay? So again, let's kind of go back to my connotation. If this is my kind of event A, and this is kind of my event B, what do I need? I need to figure out what is the probability. Remember, let's rewrite our definition. The probability of A given B is the probability of the intersection over the probability of B happening by itself. Okay? So let's think about it. The probability that the dice sum to 4 is, well, we have the number of good outcomes. We have 3 good outcomes, right? If I kind of circle those here. So that's going to be 3 over the 36 total outcomes, which is 1/12. And then the probability of both of these things happening, A intersect B, well, that means that not only am I in this red region, but also the second die is even. Turns out there's only one way that that can happen, which is this guy. So there's actually only one outcome where that's true. So this outcome is 1 over 36. And then, by my formula, the probability that A given B is this 1 over 36 divided by 1 over 12, which is 1/3, right? Bless you. So this kind of stands to reason, right, in the sense that, you know, this second die being even is one of the 3 outcomes of the overall B, right? And if I think about it, the probability of A by itself, right, what's the probability the second die is even? Well, if these outcomes are all equally likely, the probability that the second die is even is 1/2, right? But by telling you this new piece of information, oh, by the way, the dice added up to 4, the probability of that second die being even changes, right? Because I've gotten some new information, and that reflects that, okay, actually that was a less likely thing to happen than I thought, right? So hopefully this easy example makes some sense. Let's do another example with the same data here. So let's say something like, okay, what's the probability that the sum is greater than or equal to 8, given that one of the dice, we don't know which one, is greater than or equal to 4. Okay, again, we're going to call this our A, and this is our B, right? Well, what's the probability that one of the dice is greater than or equal to 4, right? My probability of B is basically saying either I'm in this world or I'm in this world, right? So actually, the probability of B is like this area here. It's 3/4 of the sample space, right? Now, what's the probability of A intersect B, right? That both of these things are true. Well, now I need to be both inside here and the sum has to be greater than 8. So if I think about it, greater than or equal to 8. So that means I'm kind of in this triangle here, right? 15 out of the 36 total outcomes. Maybe I should go back and write this as 27 of the 36, just to be super precise, right? So 15 of the 36 total outcomes satisfy both things, and so the probability of A given B is 15/36 over 27/36, which is 15 over 27, which is 5/9. Okay? So you're going to do a bunch of these kind of basic calculation things on the homework that's coming up, okay? Not too bad. Finally, let's talk about something like, what's the probability that the sum is greater than or equal to 8, given that one die is equal to 1. So here, again, the probability that the sum is greater than or equal to 8, we already kind of know. So probability that, actually we don't have to do any computation here at all, right? Because the probability that both of these things happen, right? If this is my A, this is my B, that's like saying that one die is equal to 1 means I'm either in this column or this row, and actually there are no outcomes where the sum is equal to 8, right? So the intersection here is 0, and that means the probability of A given B is equal to 0, right? Because, if I tell you that B happened, there's no way that A happened, right? The sum being greater than or equal to 8 means that each of these dice has to have kind of sufficiently enough value to get me up to 8, right? Having one of the dice equal to 1 just won't cut it. Okay, so let me stop and ask. Any questions or comments? Not too bad, right? So let's bring this into the world of, continuous sample spaces. We haven't really talked super much about this yet, but, still we're going to use our kind of geometry intuition that if I have like this uniform distribution, I can also make some similar reasoning. So similar idea for continuous sample spaces. For example, let's take two numbers, x and y, picked independently, and uniformly from this 0 to 1 interval. Okay? So let's ask something like, what is the probability that y is greater than x, given that y is greater than 1/2? Okay? So let's draw our sample space again. Here's my sample space for x. Here's my sample space for y. And this is kind of my event A. This is kind of my event B, right? So the probability of B by itself, that y is greater than 1/2, I'm going to draw that in like this, is up here, right? I know that's equal to 1/2. The probability that that y is greater than x, so I'm going to draw the line that y equals x, and then I'm going to draw the places where y is greater than x, right? So the probability that both these things happen, A and B, or A intersect B, well, what's the area of this kind of trapezoid here? Well, it's 3/8 of the whole square, right? Because the area of this little guy is 1/4, and then there are 3 of those guys up there. I'm sorry, the area of this guy is 1/8, right? So that means that the probability of A given B is 3/8 over a half, or 3/8 over 4/8, which is 3/4, right? And so, again, let's refer to the fact that before, the probability of A by itself was a half, right? That red triangle's probability was a half. Now I tell you, hey, you're in the upper half of the plane. That tells me that, since y is already a pretty big number, then it's more likely that it's bigger than x, right? So the probability goes from 1/2 to 3/4 with this new piece of information. Okay? Make sense? Okay. So let's kind of make this a little bit more general. Okay, so now I'm going to introduce a concept that we actually already kind of saw a little bit on homework too, which is called a partition of a sample space. Right? So first I'm going to kind of draw the idea. So I've got my sample space. And then what I'm going to do is I'm going to break this sample space up into a whole bunch of disjoint events. Events that don't overlap. Don't worry about the shapes of these things, doesn't really matter. I'm just going to draw them kind of haphazardly here. Right, so let's call these, B1, B2, B3, B4, B5, B6, B7. Right? So a partition is basically a set of events that, number one, are disjoint, that is, they don't overlap at all, and number two, they make up the whole sample space. Right? So if I write that more mathematically, this is a set of events B1 through Bn in a general way, such that the intersection of any of these two events is the empty set when I'm looking at different sets, and the union of these sets is the whole sample space. Right? And you can recognize that I kind of already threw this at you a little bit in one of the problems on the last homework, right? Just because it's kind of, lights flicker, or is it just me? So what does that mean? It means that, from our axiom of probability, that if I were to add up the probabilities of all of these events, it's going to be the probability of this union, which is the probability of the sample space, which is 1, right? Exactly one of these events has to happen, right? So again, for example, let's suppose that, the sample space is just people in the world, and these BIs are like, partitioning into, are you age 0 to 10, are you age 10 to 20, 20 to 30, 30 to 40, right? So those events, make up the entire sample space. You have to be in one of those classes, and you can't be in more than one of them at the same time, right? Okay, so now what we're going to do is we're going to consider some event in the sample space and think about how it may intersect with this partition, okay? So what I'm going to do is I'm going to look at I guess I'm just going to draw it on top of here. Let's suppose now I have some sort of event A, okay? So now I consider some kind of arbitrary event A, okay? Well, what I want to do is I want to compute the probability of A, okay? So what I could do is I could think about breaking up A into its little constituent parts, right? What I could do is I could add up this part of A that intersects with B1 and this part of A that intersects with B2, and so on. All of those little red pieces are disjoint, and they make up the entire set A, right? So that means, more mathematically, that the probability of A is the same thing as the probability of A intersect B1 plus the probability of A intersect B2 plus ... the probability of A intersect Bn, right? And those make up all the pieces of A, right? Because there are no more B's. The B's make up the whole sample space. So I'm looking at the intersections of A, those little red pieces, right? So the probability of A is the sum of these intersections with the pieces of the partition, okay? And now I'm going to use my little conditional probability definition from before, right? So remember that we defined a ways back, if I can find my sheet. We defined this is kind of this key definition of conditional probability. What I'm going to do is I'm going to move the denominator over onto the left-hand side and say this is the same as the sum from I equals 1 to n, the probability of a given event bi times the probability of bi. Right? And I'm just going to rewrite what's on this left-hand sheet of paper, since the probability of A intersect B over B equals the probability of A given B. Okay? And so this is really important. I'm going to put this in a box also. This is called the total probability theorem. So this is, as it turns out, useful because it relates the probability of a bigger event to the probability of that event conditioned on a whole bunch of smaller events, okay? So let me be a little bit more, and the reason that this is sometimes useful is it turns out that in the real world it's often easier to compute conditional probabilities than it is to compute big probabilities, right? So it's easier for me to say, okay, you know, I know what is the probability that the test is positive for a patient with the disease, and I know what's the probability with the test is positive given a patient without the disease, right? And then I use those pieces of information to tell me the overall probability that the test is positive for anybody that I happen to pick out of the crowd. We're going to do that example in a couple minutes, okay? So let me do a more concrete engineering kind of example, okay? So very common communication system is what you call the binary communication channel. Okay, so let's suppose that I have basically bits that I'm sending across a channel, okay? So on the sent side, I can either have a 0 or a 1. And on the received side, I can have either a 0 or a 1, okay? And often you see in communications textbooks a diagram something like this, right? So there's a little probability epsilon 0 here, and there's a probability 1 minus epsilon 0 here. And then there's a probability epsilon 1, 1 minus epsilon 1. What this basically means, it's saying that the probability that I receive 0, given that I transmit 0, is equal to 1 minus epsilon 0, okay? The probability that I received 1, when what I transmitted was 0, is epsilon 0. And the same kind of thing for transmitting a 1, right? And obviously you want to be in the case where these epsilons are really small, right? You don't want there to be mistakes when you're transmitting across the channel. But like we kind of talked about in the first lecture, these things happen, right? Basically, you have errors that come from thermal noise and atmospheric noise, and so bits get flipped all the time in the real world. And luckily, your communications devices are robust enough that they've got these error correcting codes that you don't notice that the bits are getting flipped. But it does happen, okay? And so now I could also say, let me give you some additional information. Suppose I tell you that the probability that a 0 was transmitted in the first place was 1 minus p, and the probability that a 1 was transmitted in the first place was p, right? So again, in some situations, these numbers may be the same, right? So for example, for kind of like compressed data, usually in compressed data, what you try and do is make the relative frequencies of the zeros and ones as close to even as possible, so there's no kind of bias in what's going on across the channel, right? So when you zip a file, for example, and you look at the binary bits, those bits should basically be equally distributed between 0 and 1. But then there are situations where, for example, like if you've got a fax machine, and the fax machine is transmitting, you know, bits of ink on a page where, say, black is equal to 1 and 0 is equal to white, right? So if black is 1 and white is 0, then, you know, since the pages that you transmit over a fax are usually kind of like sparse black text on a big white background, maybe this p is smaller, right? Could be a 10th or a 5th or something like that, okay? So the point is that, you know, we don't really necessarily, we also have to know kind of what's the balance of zeros and ones, right? And now I can ask something like, you know, what's the probability that I have an error in decoding? What's the probability that what I got was not what I sent? Okay. Well, I can build that error out of the composite pieces that I have, right? So let's use my theorem, right? This is like saying the probability of error overall, right, is equal to the probability of error that I transmitted a 0 times the probability that I transmitted a 0 plus the probability of error given that I transmitted a 1 times the probability that I transmitted a 1, right? These two pieces make up the overall probability of an error, right? Those are the two possible states of nature, okay? And again, you can see that as an engineer, it was easier for me to characterize these conditional probabilities in the form of this kind of butterfly chart on the upper left than it was for me to tell you, oh, the probability of error in the channel is, you know, 3%, right? Instead, now I can compute this, right? So let's think about it. This is like saying that, okay, the probability that, now I need an extra pair of hands here. I'm just going to move this back up here. So let's compute these values, right? So the probability of error is equal to probability of error given that I transmitted 0. So if I transmitted 0 and received a 1, that's an error, right? So that's this probability, epsilon 0. And the probability that I transmitted a 0 in the first place is this 1 minus p. The probability of error that I transmitted a 1 is what I called epsilon 1, and the probability that I transmitted a 1 in the first place is p, right? So my overall probability of error is this number, okay? And if p is just a half, then the probability of error is the average between these things. But if one type of bit is more likely than the other, and the behavior of that type of bit's error is more likely, is different than the other one, then I could get some very different number, right? Kind of a weighted average between epsilon 0 and epsilon 1. Okay, so let me ask, any comments or questions about this? Yes? Can I go over again this equation, right? Okay, so let's talk about that one more time. So this is motivated from this key. So let's go back to this, right? So this is this key idea that the probability of one event, and that's what this picture here is. It's like saying the probability of the red thing is the probability of each of the pieces, right? And so now what I want to do is say, okay, so in my case, I've only got two pieces, right? Either I transmitted a 0 or I transmitted a 1, right? So there's only two cases. And so the probability of overall error is the probability of error given that I'm in case 1, which is that I transmitted a 0, times the probability that I'm in that case that I transmitted a 0, plus the probability of error that I transmitted a 1, given that I'm in that case that I transmitted a 1. Okay? Those are the two pieces that make up the whole thing. Other questions or comments? You're still happy? You're skeptical? You're happy? Okay. All right. So all of this is kind of leading up to this really, I say things are important all the time, but this is really important, right? So there's this thing called Bayes' rule, Bayesian reasoning, right? And so this is something that's kind of, I think, penetrated the, pop science. You'll read about Bayes in, I was going to say Time and Newsweek, but no one reads Time and Newsweek anymore. You read it in blogs, you know about Bayesian spam filtering and stuff like that. So what does this Bayes concept mean? So Bayes' rule is kind of like the key probability concept that underlies so much of machine learning and so on today, okay? So let me talk about what that is. So Bayes' rule is the following. So a key application of conditional probability is Bayes' rule. Okay? So Bayes' rule, before I actually write it down in terms of math, so intuitively the idea is that, I'm talking about this idea that, okay, I've got this test, I've got this disease, right? So using what I just talked about, I could compute, for example, what's the probability that the test is positive, right? So let me just kind of like, so far, kind of what we know is that the probability that the test is positive, I could compute from the probability that the test is positive given no disease times the probability of no disease, plus the probability that the test is positive given that I have the disease times the probability of the disease, right? So that's great, right? But what I really care about, right, what we usually want in the real world is, what we really want is the probability of the disease given that the test is positive, right? That's what the doctor cares about, right? So we have to figure out how do we kind of invert this conditional thing, right? So it's often easy to say, okay, I know what the probability of A given B is. What you often want in the real world is that you want the probability of B given A. How do you switch those things around? Turns out to be pretty easy, okay? So let me set it up again. Let's suppose that we're still in this world where I've got a partition of the sample space. So I'm kind of splitting the world up into these possible events, okay? So we're still kind of like in this context here. So as before, we have a partition of the sample space. And now we observe that this event A occurred, and we want to know what's the probability that I'm in one of these BIs, okay? So now we observe that A occurred, and we want to know what is the probability that BI occurred given A. Right? So we want A to give us some information about which of these classes we're in, right? So for example, in this sketch, if I tell you that A happened, then I know for sure that I've ruled out B7 happening, right? That whole part of the sample space I know I'm not in if I tell you that A happened, right? So I kind of need to undo my my conditional probability here. But let's work out what this means, right? So this means the probability of BI intersect A over the probability of A, okay? That is just from our first rule, right? And now I can take apart the top and I can say, well, the probability of this intersection here is the probability of A given BI times the probability of BI over P of A. Right? Why is this? Again, remember that the probability of A given BI is equal to the probability of A intersect BI over the probability of BI, or probability of B, right? And so this here I have in the numerator, I'm just bringing this P of B over to the other side to make this thing on the top. So this is kind of a nice little avenue to get from these things, which I can often characterize in a real-world application, over to this thing, which is often what I want to actually know, okay? And if I want, so this is I think the key thing, right? So I'm going to put a box around this, right? This is basically Bayes' rule. And so these little pieces have some terminology to them, right? So the P of the BIs are what are called priors or prior probabilities. Right? The P of BIs are like saying, well, what were the probabilities before I saw any new information, right? What was the probability of each of these classes happening before I knew anything else, okay? And then the probability of BI given A are what are called the posteriors or the a posteriori probabilities. Right? So it's like saying that this is what I thought before. Now I saw that A happened, and now I update my probabilities according to that new information. Right? So before I did the test, I thought that this was the, probability this person was sick, right? Now I did the test, I observed what happened, and my a posteriori probabilities change, they rebalance, depending on the outcome of seeing this new thing, okay? Okay. So for example, if I go back to my communication channel, right, what I really care about is, I am the I'm the operator over at the other end of this communication channel, and I want to know, okay, suppose that I received a 0, or suppose I received a 1. How do I know how likely it was that the 1 is a true 1, or whether it was corrupted by being flipped, okay? So for example, what I care about is, in my communication channel, what I often care about is what is the probability that a 1 was transmitted given that a 1 was received, right? Which is exactly the opposite of what I'm telling you as the operator of the system. These things it's easy for me to characterize. This is like saying, okay, I got a 1, how much do I trust that 1, right? So now what I can do is I can apply Bayes' theorem to undo and get back to what I want, right? The probability that I transmitted a 1 given I received a 1. So let's look at how Bayes' rule applies to this, okay? Well, this is like saying I look at the probability that I received a 1 given that I transmitted a 1 times the probability that I transmitted a 1 over the probability that I received a 1. Okay, that's what this is telling me. Again, let me just kind of make it a little bit clearer that this is my B and this is my A, right? So then I flip it around to make sure it's kind of clear what's B and what's A in each of these events, okay? So I can go back and actually solve this problem, right? So before, what about this, right? So a different way of thinking about Bayes' rule is that this denominator, right, is kind of like, it's a fact, right? I'm telling you, okay, I received a 1, right? So the top part is saying, okay, well, what fraction of those outcomes came from transmitting a 1, right? So I can rewrite this slightly. I'm going to keep the numerator the same. And the denominator, I'm going to expand out to say, okay, well, how could I have received this 1, right? So one way is if I transmitted a 0. Oops, sorry. And one way is if I transmitted a 1. Okay? So you can see that, you know, this part here is the same as this part here, right? This is just kind of like a fraction saying, okay, you know, what is the ratio of this piece to the whole, okay? And I can compute each of these pieces if I were to use my same numbers from last time, right? So here I had that, okay, the probability that I received a 1 given that I transmitted a 1 was 1 minus epsilon 1. The probability that I transmitted a 1 I called P earlier. And then the other part, the denominator, is probability that I received 1 given that I transmitted a 0 is epsilon 0. The probability that I transmitted a 0 is 1 minus P. And then the probability here is just copying from the top. I can see that this has got to be, you know, less than 1 because, you know, this denominator can only be bigger than the numerator. So this kind of thing is widely used in electrical engineering because you often want to determine the most likely signal that you transmitted by looking at what you received, right? And so if you're going to take a course in communication systems, for example, following on from this course, you're going to see a lot of these kinds of computations because, you know, things can get even more complicated. Instead of just having 2 bits, you could have, you know, the probability that I transmitted this code word and the probability that I received a given code word, right? So those kinds of things can get a little bit more complicated. Let me try to make it a little more, I know this is a little bit of a weird abstract example. Let me bring it down to a more real-worldy example, right? So this is something that happened, or not happened, it happens to me all the time, right? So I get a lot of email, and so you guys all know about spam filtering, right? Respite and so on. So it turned out that for many years, it seems to have tapered off in the past few years, but I used to get a ton of Russian language spam, well, Cyrillic letters I couldn't read. And so, you know, what I want to know from a spam filtering perspective is, you know, what's the probability that my email is spam given that it's in Russian, okay? So Bayes' rule tells me that, and this is something that, you know, I don't necessarily know from the outright, but I can use Bayes' rule to rearrange this equation. Right? And the things on the right-hand side of the equal sign are easier for my email program to keep track of, right? So it looks at all the email that comes in, and, you know, I am dragging stuff into my spam folder to train the algorithm about what I think is spam and what's not, right? So certainly my mail program can understand overall what's the probability of spam, right? What's the ratio of spam mails that I get to real mails. It can also reason about what's the probability of Russian males that I get, right? Probably not that many, but overall this is the fraction of Russian males that I get. And then it can say, of the males that I've dragged into my spam folder, what's the probability that those were Russian, okay? And so all these things basically can be trained by a combination of scanning my mailboxes in a passive way and my telling the algorithm, this is spam, this is not spam, okay? And so then if it turns out this probability is high enough, then my mail program may just apply a rule that says, okay, any Russian mail that comes in is spam. It's 90% likely to be spam, so I'm going to put it in the spam folder, right? And so if you've ever used a spam, I mean, I guess it's actually been, well, I don't know. I mean, like, used to be in the early days of mail programs and automated spam filtering that you would really have to spend a lot of time training your spam filter, right? But these days, I find that I don't have to really do that much at all. It seems like the respite spam filter catches all of my spam, and it catches some of the emails that I, maybe are legit, but that I don't care that much about. And it very rarely categorizes something as spam when it's not, right? And so that's kind of like what you want to do, is you want to train your algorithm to do a good job, okay? So let me do another example. Again, I keep on coming back to this test and disease. So let's kind of think about that, again, as the real world situation, right? So suppose I'm trying to do some sort of a medical testing scenario, okay? So medical testing. Okay. So we do a test T to see if a patient has a disease D, okay? And so what I want to do is ultimately I want to characterize, we eventually want the probability of disease given that the test is positive, okay? That's kind of like the natural thing that the doctor wants to know, to be able to tell, okay, well, if the test is positive, should I take action or not, right? And so how would you get all the probabilities that you need to be able to come up with this number, right? Well, probably what you'd do is you would give the test to a lot of people that you know are sick and a lot of people that you know are healthy, maybe through other means, and you'd collect these statistics, right? So let's suppose that we have gathered this information. The probability that the test is positive, given that I have the disease, is 0.99, okay? And that means the probability that the test is negative, given that I have the disease, is 0.01, right? Those two things have to add up to 1 because those are the only two possibilities, right? Now I also have to know the probability the test is positive, given that I don't have the disease. And let's suppose that probability is 0.05, right? That means that, occasionally the test goes off for people that don't have the disease. But most of the time it does what we want, right? The probability that the test is negative, given that I don't have the disease, is 0.95. So on the surface, this seems like a pretty good test, right? And again, you probably have heard of these kind of categories of making mistakes, right? So the probability the test is negative when the disease is present is what you'd call a false negative. And the probability that the test is positive when you don't actually have the disease is called a false positive. Okay? So let's see now what this number is, right? I want to know what the probability, and also the final thing I have to be able to kind of reason about the overall probability is I have to know what is the kind of expected probability of the disease across the whole population, right? I have to know how common are each of these classes, right? So let's suppose that, the probability of having the disease is 0.01, or 0.001, very, very rare, okay? So now I can go through and I can compute, okay, so what's the probability of disease given that the test is positive, okay? So again, I'm going to apply Bayes' rule, right? I'm going to say the probability that the test is positive given the disease times the probability of the disease over the probability that the test is positive. So first I have to compute, what is the probability that the test is positive in the first place overall? Well, I use this kind of total probability theorem. I think I can break this up by saying it's the probability that the test is positive given that I have the disease times the probability of the disease plus the probability that the test is positive given no disease times the probability of no disease. Okay, well now I can multiply these numbers together, right? So this number, I have a true positive, is 0.99. The probability of disease is up here, that's 0.001. This number, positive test but no disease, is 0.05. And the probability that there's no disease is going to be 1 minus this top part, which is 0.999. Okay? So I work this out, right? And what I'm going to get is, unfortunately I didn't bring my calculator, but I know the result. The result is going to be, let me just write this overall, that this part here is what I need in the numerator. This part here is what I have in the denominator. I did the computation at home. And what do I get? 0.019. Now, let's think what that means, right? That means that, I should make sure this is, I'll make sure I don't confuse you here. So that means that if the test is positive, the probability that I have the disease is 0.019. That's like super small, right? I mean, this is not what I expected. What I expected is that if the test is positive, it gives me pretty clear evidence that this person has the disease, right? But what went wrong, right? What went wrong is that the test is going to go off positive for some small fraction of healthy people, right? But there are so many more healthy people than sick people that that number of false positives is going to totally outweigh the number of true positives, right? It's very unlikely that I have a true positive because the disease in the first place is very unlikely, right? So that means that this is actually a pretty crappy test, right? I shouldn't use it for any sort of diagnostic purpose. What would I need to do to make this test better? Well, what I need to do is I can't change the probability of disease, right? That's something that's fixed in the world. The only thing I can do is try to make a better test. What I really should want to do is I want to drive this number to be much, 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 much lower than it is, right? And it turns out, for example, that if I were to turn this down to, if we made false positives much less likely, and I'm going to underline much. For example, let's suppose that the probability of a positive test given no disease was more like 0.0001, right? Then I would have some hope that the probability of disease given the positive test, I could work out the math, and that would be, 0.91, right? So again, you as a user can tell the drug companies, okay, I'm not gonna, I don't care about the test unless it's got a false positive rate of X, right? And these kinds of calculations have real implications in terms of, drug testing, medical treatment, weighing evidence, DNA testing, right, stuff like that. In fact, there was a similar kind of related issue a couple years back about mammograms, right? There was a question about, okay, so if you do a biopsy, or was it mammogram? I think it was biopsies. Basically, something like saying, oftentimes these, no, it was mammograms. I think if you have a mammogram that the person reads as positive, they may go off and get a biopsy, and a biopsy is a very uncomfortable, invasive procedure, right? And it turns out that in many cases, no one had the disease in the first place, right? So the debate, the kind of popular debate surrounded the question about, like, given the false positive rate of mammograms, should you recommend that you get them every 2 years or 5 years or whatever, right? So because it means that, you know, if you're willing to tolerate more false positives, that means you have more invasive biopsies. So there are real social questions that kind of underlie these issues. And again, if you're kind of like a knee-jerk reaction and say, well, you know, if you're like a politician, say, well, this test sounds okay, let's approve it, turns out that there are real kind of real-world implications for it. So, so it's kind of interesting stuff. You know, there's definitely intersections between probability and public policy, stuff like that. Okay, so let me pause and ask. Any questions or comments? All right, so now I have to do the thing that you always do at this phase of a probability class, which immediately destroys all your intuition about conditional probability, but we're going to do it anyway, right? So this is called the Monty Hall problem. So raise your hand if you heard about the Monty Hall problem. A few people. Okay, so if you haven't, here's the story. So there was an old TV show called Let's Make a Deal, okay? And the premise was that there were 3 doors, and you picked a door, and you were hoping that what was behind the door was a car, okay? And so the whole premise of the show was playing at the suspense about whether or not you picked the right door, right? So the setup of the Monty Hall problem is that the host knows what's behind the doors. You pick, say, door number 1, okay? Now the host opens door number 3, and what's behind door number 3 is a goat, okay? So you know that the car is not behind door number 3, okay? And then the host says, okay, do you want to switch which door you picked, okay? And it seems on the face of it that nothing can have changed, right? Just because you saw the goat shouldn't change anything, but it turns out that by conditional probability and in the real world it does. So let me kind of give you some intuition here, okay? So the Monty Hall problem. And I'm going to explain it in the simplest way I know how, even though it is very counterintuitive. So, you know, let's say that you pick door number 1, okay? And now let's kind of make a list of, okay, so what are the possibilities here, okay? So a priori we assume that the car has equal probability, 1/3 of being behind each of those doors, okay? So there's the car, the true car, there's the door that the host opens, and then there's the probability of the host opening, you know, this door given where the car is, okay? So let's look at the 9 possibilities. The car behind door number 1, the car behind door number 2, the car behind door number 3, host opening 1, host opening 2, host opening 3. And remember, in all these situations, I picked door number 1, okay? Now the host is never going to open my door, right? The whole suspense is about whether my door is correct or not, right? So the host never opens door number 1 in any of these cases, okay? So I'm just going to put 0 down for the host ever opening door number 1, okay? Now if the car actually is behind door number 1, then the host basically can open either of the 2 doors. And let's suppose the host does that with equal probability, right? The host has no reason to care about which door they open. They both contain goats, right? So he can open whichever door he wants, okay? Now, if the car is behind door number 2 and I pick door number 1, then the host can't open door number 2 because it's got the car behind it, right? So the only thing the host can do in that case is open door number 3, right? The remaining door that he knows has the goat, okay? And the same way, you know, if the car is behind door number 3, the host is not going to open door number 3. He's only going to open door number 2, which is the one that contains the leftover goat, okay? And so now, let's use the world of conditional probability to say, okay, so I pick door number 1, the host opens door number 3, okay? So now, what's the probability that the car is behind door number 2 given that the host opened door number 3, right? So this is basically the equivalent of switch, right? I picked door number 1. What's the probability that I chose incorrectly and that the car is actually in the other door, okay? Well, let's operate with Bayes' rule here. So actually, this is not even Bayes' rule. This is just like straight out conditional probability. So this is, again, like A and B. So this is the probability of A and B over the probability of B, So what's the probability that the car is equal to 2 and the host, and the host is picked 3 over the probability that the host pick 3. Okay? Well, again, let's unpack this, right? The probability that the host equals 3 is the sum of the probability that the host equals 3 given the car equals 1 times the probability the car equals 1 plus the probability that the host picked 3 given the car is equal to 2 times this probability plus the probability that the host picked 3 and the car is equal to 3 times that probability, right? So each of these probabilities is 1/3, right? That's kind of like the prior probabilities of where the car could be, right? So now let's go back to my table and say, okay, probability host pick 3 given car was 1 was 1/2 times this probability is 1/3. Probability host pick 3 given car was equal to 2 is 1, right? The host is forced to open the door in that case. Probably the host opens door number 3 given the car is behind door number 3 is 0. He's not going to do that. Right? So what do we got? We got 1/6 plus 1/3 is 1/2. Okay? Now, so that's the denominator of this thing. What's the probability that the car is equal to 2 and the host is equal to 3? That is this row of the table here, right? That is 1/3. So what's 1/3 over 1/2? It's 2/3. And this is the counterintuitive part. This basically says that if the host opens door number 3, the probability is 2/3 that the car is actually in the other door. And so I should switch if I'm given the opportunity to switch, okay? So this problem has been around forever. Hold on a second. So this problem's been around forever, and it created a huge amount of debate. So there was a newspaper columnist, Marilyn Vos-Savant. She used to publish in this Parade magazine. I remember when I was a kid, right, there would be like a weekly brain teaser, right? So she gave the Monty Hall problem, and she laid it out almost exactly like this, and said, okay, well, you should switch, right? And there were mails and mails to the papers saying, this woman is an idiot, she doesn't know what she's talking about, nothing can change, right? The probability has to be 1/2, right? Switching shouldn't make any difference between staying, right? These things came from, professors of mathematics at all sorts of embarrassingly good universities and so on. But, things don't lie. And before I take questions, let's just switch over for a second to simulation. If you don't believe me, believe the internet. So here is a simulator, right? Let me see if I can make this font a little bit bigger. Close my ad here. So basically the idea here is that, if I pick my door and the host reveals the goat, right? So now I have, the opportunity of keeping or changing, and I have the opportunity of saying, okay, I can run the simulation, either keep or switch, right? So if I say change the choice, and let's do this 500 times, watch the green bar, right? This should settle to around 2/3 probability that I win by switching the door, right? And in a similar way, if I were to say, look, I don't care about probability, I'm going to stick with door number 1, in that case, and we're almost done with simulating here, so we're up to, 400 okay. So this was the total of the 500 trials. In 346 cases, which is 69%, switching was the better choice, right? Let's suppose that you don't believe me and you say, okay, I'm going to keep the goat. I'm going to keep door number 1. What happens there? All right, let's simulate this again. So let's reload. So now I'm going to, again, pick door number 1. This door gets opened, and I'm going to keep the choice, right? So let me run that 500 times. Odds are that the goat, the red bar, is behind my door, right? So it's very weird, and of course this is why the show had so much tension, right, is that people were like, oh, should I switch or not, right? So I'm going to close this ad. You guys don't need to be drinking Michelob, I'm sorry. So that's the story, right? Strange but true. All right, So questions about this? Yes?
So it's the probability that, you said like probability, that probability the car is behind door 2, given he shows you door 3.
Yes.
Is there like another given he shows door 1?
So let's go back to my document camera here. So the setup here in the one that I did was I picked door number 1, the host opened door number 3. Right, so this is like kind of a simple version of the problem. So it turns out, it doesn't really matter whether I picked door 1 or door 2, as long as the host opens another door and shows me a goat, right? So kind of us fancy mathematicians say without loss of generality, let's just assume I open door number 1 and the host opens some other door, right? Should I switch or not, right? Turns out that if I just relabel the doors, nothing changes, right? Yeah. Other questions or comments? If you don't believe me, you can run your simulations yourself and you'll be convinced, right? Other question?
Just a small question. So in simulation, if you still be pursued at random, will that affect the possibility resulting?
So, I mean, the simulation is random, right? And here in the simulation, the host is picking the other door with 1/2 probability when he can, right?
But in computer, it's mechanical with pursued at random. Nothing can happen.
Well, so let me put it this way. So it turns out that in this statement of the problem, you can't do any worse by switching, okay? So if it turns out that the host, for some reason, pathologically so when he has the option of opening, so say you chose the car and the car is behind door number 1, the host can choose either door 2 or door 3 to open, right? And if he opens those with unequal probabilities, it turns out that, you can do a little bit worse, but you can never do better than, 1/2, right? So basically, you should always switch even if the possibilities are unequal, right? And a lot of mathematical analysis hinges on how you pose the problem, right? So for example, here we had to be careful to say that the host is kind of obligated to open a door and show you a goat, right? If the host doesn't have that, if the host has some discretion, or if the host has no idea what's behind the doors, then the whole mechanics of the problem change. And so you can find lots and lots of variations on this Monty Hall problem depending on exactly how it's stated. And somehow that's the source of sometimes a lot of the confusion is, oh, does the host have to open a door? Does he have to open this? But anyway, that's the story. All right, so before we go, there was a question about the last homework, which is now comfortably due. So let's do that real quick. I'm not going to do the whole homework, but let's suppose that we're doing this problem with the X-force, okay? So there are 6 X-force members. And then there are, 3 cool members. Right? So the first question was, how many different ways are there for these 6 members to stand dramatically left to right in the poster, right? So if I imagine that there are basically 6 slots for the X-force, there are 6 choices for the left-hand slot, 5 choices through a remaining slot, 4, 3, 2, 1. So the answer is 6 factorial, which is 720, okay? Okay, easy. So now let's suppose that we are going to put these X-force members into 2 cars, right? One car is a 4-seater, and one car is a 2-seater, okay? How many ways are there to choose 4 of the 6 people to sit in the SUV, right? So I mean, again, there was a comment at Piazza that was like, wow, this number is a lot smaller than I thought it was. It turns out to be pretty small, right? So how many ways are there for me to choose the 4 people who ride in the SUV? And I don't care about order, right? Just the collection of people that are in there. Well, there are 6 choose 4 ways, right? And that's going to be 6 times 5 over 2. Only 15 ways for that to happen, right? Remarkably small. And if you don't believe me, it's easy to enumerate what these possibilities are, okay? Then the question was, what's the probability, assuming that everything is fair, of the 3 cool people sitting in the same car? So in this case, the cool people, let's say they're A, B, and C, we know that they're in the 4-person car. How many ways are there for that to happen? Well, that means that there are 3 possible ways to fill this extra seat, right? Could be D, could be E, could be F. So it's going to be 3 over 15th, which is 1/5, okay? All right. Questions about that? Now, what happens if we have two four-seaters, okay? So now there's going to be some extra spaces in the cars. Okay? So first of all, how many overall possibilities are there for allocations between the cars, right? Turns out there are three ways this could work, right? Either I have 4 people in the first car and 2 people in the second car, I have 3 people in the first car, 3 people in the second car, or I have 2 people in the first car and 4 people in the second car, right? So how many ways are there for each of these things to happen? Well, this one is 6 choose 4, right? And that's 15, which we just computed. This one is how many ways are there to choose 3 people from 6? 6 choose 3 is 6 times 5 times 4 over 3 times 2 times 1. So there's 20 ways for this to happen. And 6 choose 2 is the same as 6 choose 4, which is 15. So there are 50 overall ways that this can happen, okay? How many of these then are favorable, right? So how many outcomes have A, B, and C in the same car, okay? Well, let's think about what could happen in SUV number 1, right? So in SUV number 1, I could have A, B, C, and then the other options are D, E, F, or blank, right? So there are 4 options in car 1, and the same thing could happen over here in car 2. They could all be in car 2. So I have 4 plus 4 over 50, which is 8 over 50, which is what? 4 over 25. Okay? Wham, bam. Speedy, question? I write these questions, yes. They come out of my head, fully formed.